Well, hello, welcome again to our journey into complex analysis, and we were looking at improper real integrals, and I mentioned that in some cases we need a slightly stronger inequality to complete the bounding argument, especially with integrals involving Cauchy principal value. And to do that, we use this little trick called Jordan's lemma. Now the lemma itself is just this little bit here. Sometimes people refer to this down here as Jordan's lemma, but it's really a theorem that follows from Jordan's lemma, but we often use the term Jordan's lemma to refer to the theorem itself. So Jordan's lemma simply says that for r bigger than 0, this integral, the integral from 0 to pi of e to the minus r sine theta d theta, is less than pi over r. It's just a little technical result. And the way one does this is firstly to use the symmetry of the sine function and just to integrate from 0 to pi on 2 and then double it, which follows immediately from the symmetry of the sine function. And then to note that for theta in the interval 0 to pi on 2, then sine theta is bigger or equal to 2 on pi theta. So if you just draw a picture, you'll see that's fairly obvious. That means this integral then is less than twice. We can simply replace the sine theta with theta times 2 on pi. This integral now is easy to do, so you do it, and you simplify it a little bit, and then e to the minus r is less than 1 for r positive, and so this is less than pi over r. Now the main theorem, which as I said is sometimes referred to as Jordan's lemma itself, says that if you've got f, which has its singularities in the upper half plane, and c is the standard semicircular contour of radius r, described above, then if the modulus of f is bounded by this m sub r, by some constants, which depend on r, at all points z on the contour, then if this m sub r goes to 0, that is, if the function's going to, the modulus of the function is going to 0 as r goes to infinity, then the integral as r goes to infinity of f of z times e to the I z dz is 0. Looks a slightly odd thing to use, but it is quite useful when you're dealing with trig integrals. So the proof of this, well, you just substitute z as r e to the I theta in and to the integral, and then you use Jordan's lemma that we had above, and I'll leave you to complete the details as an exercise if you're interested in doing that. So let's have a look at an example. We're going to work out the Cauchy principal value of this integral. You can see that the dominant term on the top is x and x squared on the bottom, so this won't converge completely in the usual sense, but it will have a Cauchy principal value. And here is the worked solution for this problem, and gives an example of using Jordan's lemma. So here's our integral, and we, of course, as soon as you see a sine x, you want to replace that with an exponential. That's very important when you're doing all of these sorts of problems. That makes the bounding arguments much easier if you can replace this with an exponential. So sine x is the imaginary part of e to the ix. And indeed you could take that imaginary part out the front because x is real here. Now that tells us what we should consider then. So we simply look at this corresponding complex integral. You just replace the x's with z's everywhere. And usual contour, we're going from minus r to r and then around the semicircle home again to give us a closed contour. And I'm going to let g of z be the integrand here, the whole integrand. Now, as before, we find the singularities. Inside gamma, this only has one singularity in gamma, which is at minus 1 plus I. You just solve this equal to 0. And again, it's going to be a simple pole, which you can see because this factors as z minus alpha, z minus alpha bar. And so we can get the residue by just doing the usual, multiply the g of z by z minus alpha and take a limit. Now remember, this term here is not 0, so you evaluate it, you get alpha e to the I alpha, and then you use L'Hopital on what's left. So you differentiate that, you get 1, you differentiate that, you get 2z plus 2, plug in z as alpha, that's 2 alpha plus 2, and finally I plug in the value of alpha, which gives me this. So we can multiply this by 2 pi I to get the integral j, which just produces this here. So I've got a minus 1 plus I copy here. You get e to the minus 1 is your 1 over e here. And then e to the minus I is cos 1 minus I sine 1. Now we can apply Jordan's lemma with f of z to be z over this function. And using the second triangle inequality again, for z on this semicircular contour, we get this bound. And that clearly goes to 0 as r goes to infinity. So by Jordan's lemma, we can say that the integral along the semicircle of f of z times e to the iz goes to 0. And that does the bounding argument for us. So as r goes to infinity, then our integral that we had is just the imaginary part of the value we got from this j, which we calculated before. And I just pull off the imaginary part of this and we get pi over e cos 1 plus I sine 1. Now I wanted to do an example using some logarithms, and we're going to, I'll just toss this extra one in here. We're going to work out the integral 0 to infinity of log x over x squared plus 1 squared dx. Again, I don't know of any elementary way of doing this. There may be some clever way of solving this, but we're going to do it using complex analysis. And we're going to need to, in fact, have another branch, another type of contour to do this. Notice this is going from 0 to infinity. So it's improper at both ends because it's improper at 0 and it's improper at infinity as well. So here's the worked solution of this, and as you'll see, it requires a bit more work than we had to do before. Firstly, I need to get our complex integrand, so I'm going to let f of z be this log with a little tilde over the top of z on z squared plus 1 squared. Now this log tilde z has a branch cut along the negative real axis when the argument of z is minus pi on 2. So we want our branch cut of log to be then down here in the picture, so that it's well away from the 0 to infinity along here. So we're taking a slightly different branch cut, and that means that the argument, this arg tilde, perhaps with a small a there, arg tilde is between minus pi on 2 and 3 pi on 2. Now our contour is going to be slightly different. Because we've got troubles at 0, I want to hop over the origin. So my contour, capital gamma this time, we're going to go around the semicircle as usual, so we're thinking of r as large. We're then going to go across here to some point minus epsilon, where epsilon is small, so we're thinking of r bigger than 1, say, and epsilon less than 1, epsilon is small. Now we hop over the origin. We want to avoid the origin because the origin is the singularity of the log function. So we hop over that, move along here, back to home again, and there's my closed contour capital gamma. Where we're thinking of r as large, well, r's at least 1 and epsilon's between 0 and 1. Epsilon is small. Now this f has a pole of order 2 at z equals I. Remember, it was z squared plus 1 all squared, so it's got a double pole at I inside the contour. So again, epsilon's less than 1. There's the and r is bigger than 1, so we arrange these so that our singularity is inside the contour. Now it's a double pole, so to get the residue then, we have to take the function, multiply by z minus I squared, take the first derivative, and then take the limit. Now this is not so bad to do because I can factorise this as z minus I squared times z plus I squared and then cancel. So I just get the derivative of this log z on z plus I squared. which I have to do by the quotient rule. We just differentiate it by the quotient rule and we take a limit. Now if you plug in z equals I into this, then and simplify, you get this expression here. Just one little thing here, you're going to get the log of I, this log tilde of I, well that's going to be I pi on 2. That's where that's coming from there. And when you simplify this mess, it just turns out to be I on 4 plus pi on 8. So you multiply this now, multiply the residue by 2 pi I, and that gives me the integral of my f of z. Simplifies down to pi on 4 minus 2 plus I pi. Now we have to worry about what on earth's going on this contour. So we're going to firstly look at what's happening on the big semicircular contour. And here's where the analysis gets a little bit more fiddly. So this log tilde, the definition of this is of course log of the modulus of z plus I times this funny argument, which is measuring between minus pi on 2 and 3 pi on 2. And you want the modulus of this, which is the square root of the, and our z is on gamma r, so I can replace mod z with r. We get this expression, and the biggest this can be is pi on our contour, because the contour is going around this way. So this is less than that plus pi squared, and then I can say that this is less than log r squared, provided r is bigger than e to the pi. So I'm saying pi squared is less than log r squared, that is pi is less than log r. So if r is bigger than e to the pi now, we can say this quantity is less than root 2 log r. So using our ML estimation lemma, the size of this integral along gamma r is less or equal to, it's root 2 log r. That's for the logarithm, and then we get r squared minus 1 all squared by the second triangle inequality again, times the length of the contour, and then we get an r to the 4th on the bottom and an r log r on the top, and that goes to 0 as r goes to infinity. Now similarly, we need to worry about what's happening along this contour. So along gamma epsilon, again, we want z on that, so the modulus of this is less or equal to, now all we do is here, I just replace from on the top, I'm just going to replace the r with 1 over epsilon, so epsilon has to be less than e to the pi, so we assume epsilon's less than 1 anyway. And then the bottom's going to be 1 minus epsilon squared. We could have epsilon squared minus 1, doesn't matter because you're squaring it. And then log of z is log of 1 on epsilon. So we're using what we had above, just replacing r with 1 over epsilon. And then using our ML estimation lemma, that's less or equal to the length of the contour times this quantity here. And ln 1 log 1 over epsilon, log hat 1 over epsilon is just ln 1 on epsilon. And now if you take a limit as epsilon goes to 0, then the bottom's going to 1, the top we've got epsilon times, well, log epsilon, roughly, take a minus out, and this then is going to go to 0, as epsilon goes to 0 from above. So that bit goes, so the bits around these semicircular contours goes to 0. I want to relate what's going on over here to what's going on over here, because the original integral went from 0 to infinity, so I don't want to be over this side, I want to go from 0 to infinity. So we look at the integral now along this part of the contour here of this, and we can replace x with minus x, and we're going to get this because we'll get a negative which will flip these around from the change of variable, and we get this expression. Now the log tilde of minus x is I pi plus log x, because it's just log of minus 1 x, so that's log of minus 1's I pi plus ordinary log x now. Now as epsilon goes to naught and r goes to infinity, then we have I pi times this integral plus twice the integral we're looking for, because we've got yep, so we end up with this here. So I'm just splitting this up into 2 bits. So I get I pi times 1 over that, plus I get this one plus the original integral from naught to epsilon on this side. That gives me 2 of those, and that's got to equal the value of j we worked out before, and that's pi on 4 minus 2 plus I pi. And if we now just equate the real parts from both sides, that's the imaginary part here, that's the imaginary part here, equate the real parts, and we end up with I is minus pi on 4. So that's a nice example of evaluating with some logarithms. So might like to try as an exercise to do similar one. Here's an interesting challenge problem here to do log of x squared on x squared plus 1. So we're moving the square from the bottom up to the top, from naught to infinity. And finally, in this little section, we can look at integrals along branch cuts, integrals involving x to the alpha, log x, etc., etc., involve careful analysis because of the idea of branch cuts. And so we'll have a look at this one. Now, of course, you could solve this by making a change of variable and just put y squared equals x, and then it turns into a much easier integral to evaluate. However, I wanted just to show how to deal with these branch cut integrals. We're going to do it. It's very similar to the logarithm. We're going to, there's the problem, the integral here we were given. We look at the corresponding complex integral, and we take a branch of z to the half again along the negative imaginary axis. And the contour we're going to integrate on is the same as we had before. It's, you go around the big semicircle, across here, around here, back to here, and we're going to have epsilon between 0 and 1, and r is bigger than 1. Now this function, f of z, which is z to the half on 1 plus z squared, is a simple pole in gamma at z equals I. Here it is here. Z equals I is our simple pole. We can get the residue the usual way. We plug this in, and then I to the half, remember the definition of this is e to the half log I, and if you simplify that you get e to the I pi on 4 over, and you've got an over 2i. So multiply by 2 pi I to get j, and simplify gives me this expression here. Now the bounding argument's a little bit easier here. On the semicircle, the big semicircle, you do the usual. The length of the semicircle is pi r, and the maximum modulus is r to the half on r squared minus 1. That's for z on gamma r, and that goes to 0 as r goes to infinity. On the little semicircle of radius epsilon, well, once again, its length of the contour is pi epsilon, epsilon to the half. Now the absolute value of epsilon squared minus 1 is 1 minus epsilon squared, if epsilon's between 0 and 1. And so once again, this goes to 0 as epsilon goes to 0 from above. Now again, we need to connect together. We need to relate this bit to this bit. So the bit on the left, this one, again we make a change of variable. We'll replace x with minus x, flips these around, and we get this expression here. Now minus x to the half, we have to go back and think about what that means. That by definition, that's e to the half log tilde minus x, where we're taking the branch of log along the negative imaginary axis. So this is the log of minus 1, which is I pi, plus log tilde of x. And e to the I pi on 2 is just I. and then e to the half log x is just going to be x to the half again. So I can then write this one now as just I times that integral. And now we add everything up. So j then is the integral we get, the one we started with, that's the bit along here, that's going to be x to the half, plus the bit along here, which was I times x to the half, plus the two semicircular integrals, and these go to 0 as r goes to infinity and epsilon goes to r goes to infinity, epsilon goes to 0 from above. Finally then, we can say that we have, this is the value we worked out before for this j, and that's got to equal 1 plus I times this integral we're looking for, and if you just cancel both sides you get the nice result here that this is equal to pi on root 2. And as I mentioned, you can do this of course by other means. You could make a change of variable here and not have to do all this, but if we're dealing with more complicated contour integrals involving branch cuts and powers up here, like for example a quarter or something, then this is a more convenient way of solving these sorts of problems.